In this video tutorial, we're going to be discussing reciprocating compressors. And to begin with, we're going to talk about the function of the reciprocating compressor, and we're going to relate that function to its pressure-volume diagram. So at the top of the screen here, we have an image of our compressor cylinder, and directly beneath we have the corresponding pressure-volume diagram. So with the cylinder resting in its current position, we can see that we've just expelled all of the air out of the cylinder. There is a small amount of air remaining in the cylinder, and that's because when the cylinder head moves forward, it's not able to expel all of that air. We'll be discussing this more later on because this is defined by something called the volumetric efficiency. So what we have left in the cylinder here is what's known as a clearance volume. So here we have indicated a clearance volume, and that clearance volume is depicted by this small distance here. Now, as we can see from our pressure-volume diagram, that also corresponds with this volume here. And it accounts for the fact that our pressure-volume diagram, or our indicator diagram, is actually shifted to the right. It doesn't start at a volume of 0. Now, although we're starting in position 3 here, what's going to happen is as the cylinder retracts, we're going to draw air into the cylinder. And the way that this happens is our inlet valve here, which is going to be spring-loaded, is going to open and allow air in to the cylinder body here. Now note that at position 3 we have a very small volume of air, but the pressure of that air is very high. We've pressurised the air, but the air that remains behind, or the clearance volume, is still at high pressure. So before we can start drawing new air into the cylinder, we need to allow that pressure to drop. Now, as we see on our pressure-volume diagram, moving from position 3 to position 4, we have a decrease in pressure and an increase in volume. And that continues to happen until we reach our inlet pressure at position 4. Now, what we see here is an idealised pressure-volume diagram, because if the ambient air outside the cylinder was at the same pressure as the air inside the cylinder, then our spring-loaded inlet valve wouldn't be able to open. So in actual fact, what happens is we create a partial vacuum. So the pressure is going to drop slightly below the inlet pressure before the valve opens, and then we see a recovery like so. So moving from positions 4 to position 1, we create a suction effect, the piston head retracts, and we create suction drawing fresh air into the cylinder. When the cylinder is fully retracted, we'll be at position 1, meaning the cylinder body is now full of fresh air. Now, the purpose of our compressor, or our reciprocating compressor, is to compress the air inside the cylinder. So, as our piston head begins to move forward again, we're going to decrease the volume of the air and we're going to increase its pressure. Now, once again, we see this on our pressure-volume diagram. We have a decrease in volume and an increase in pressure until we reach our delivery pressure. So moving from position 1 to position 2, before we reach that delivery pressure, both our inlet valve and our outlet valve are going to be closed. Essentially what we have is a sealed cylinder, so the piston head moves forward and pressurises that air. Now, it isn't until our delivery pressure is reached that our spring-loaded outlet valve can open and the pressurised air is going to be delivered into the air receiver or into the system. Now, once again, as we mentioned before, a small amount of pressurised air is going to remain in the cylinder. We're unable to expel all of that air, and so the cycle continues. So we've already mentioned our clearance volume. That's the volume of air that's left behind. But we have two other volumes labelled on our diagram. We have the swept volume, and that's the full volume that the piston head travels through the piston body. So it corresponds with this distance here. And as we see from our pressure-volume diagram, that corresponds with the change in volume moving from position 3 to position 1. It's basically the maximum volume, or the maximum sweep distance, for the piston head inside the piston body. But we do have another volume indicated on there, and that's the induced volume. And that's essentially the amount of fresh air that we're drawing into the cylinder. Note that as we move from position 3 to position 4, or this shorter distance here on the PV diagram, we're not actually drawing fresh air into the cylinder. What we're doing is we're decreasing the pressure of the volume that remains, or our clearance volume, until we reach such a point that that pressure is sufficiently low for the inlet valve to open and fresh air to be drawn into the cylinder. Now there is one other important thing to know, and that relates to when we're delivering the high pressure air, so when we're moving from position 2 to position 3. Now for similar reasons as discussed when moving from position 4 to position 1, in order to cause our outlet valve to open, we have to exceed the delivery pressure slightly. So we exceed the delivery pressure slightly, and in doing so our outlet valve can open, and then we see a recovery so that the air is still delivered at our delivery pressure. So what we see there in terms of a pressure volume diagram is an idealised pressure volume diagram. Now I'm going to reduce that image slightly and I'm going to keep it on the screen because as we work through a practical example, we're going to be referring to this diagram in order to determine things such as our swept volume, our induced volume and our clearance volume. And as we work through this example, we're going to be calculating various parameters such as volumetric efficiency, polytropic work, isothermal work and isothermal efficiency. Okay, so I've reduced the size of our diagram, but I've kept it on the screen there for reference. I've also added quite a lot of information here which I'm going to take you through before we do any calculations. Now in the top left hand corner I've listed some variables. The first variable I've listed is P del, or the delivery pressure, of 10.75 bar, and I've also listed the inlet pressure P in as 1.01 bar. Now 1.01 bar is basically atmospheric pressure, so we have atmospheric air entering the cylinder, we then pressurise that air until it reaches 10.75 bar, and then we deliver that into the receiver or into the system. I've also noted some information about the cylinder itself. First of all, I've noted that we have a clearance volume of 0.25 decimeters cubed. Now there's 10 decimeters in every metre, so as we go through this tutorial we're going to need to convert that into meters cubed. But quite often for compressors we do have volumes specified in decimeters cubed because they tend to be cleaner, more manageable numbers. So our clearance volume then is 0.25 decimeters cubed, and that corresponds with the small volume here after we've expelled all of our air into the pressure receiver. I've also indicated the swept volume, which under ideal circumstances would be the amount of air that we draw into the system, because it corresponds to the full distance that the piston head travels through the piston body. I've also specified the polytropic index. Now what we're going to look at here is how our polytropic processes differ from our isothermal processes. Now just as a reminder, an isothermal process is a constant temperature process. And we're not trying to generate heat in this system, we're trying to generate high pressure air. So the absolute ideal circumstance would be if we had an isothermal compression, because we would be creating the maximum pressure increase as we decrease the volume of our air. However, as we're going to see, we don't have an isothermal process, instead we have something called a polytropic process. So our N value there of 1.19 is the polytropic index for both our compression and our expansion. We're accepting that the temperature of the air does change when we compress and expand that air. So essentially it means we require more work to compress our air than if it was an isothermal process. We need to compensate for those temperature changes. I've also specified capital N, which is the rotational speed of the motor that's driving our compressor. So every minute our compressor is doing 450 cycles. So our piston head goes in and out 450 times every minute. Now there's a number of things that we're going to calculate here. We're going to calculate the volumetric efficiency of our cylinder. We're going to calculate the polytropic work involved in compressing our gas. We're going to calculate the isothermal work involved in compressing our gas. And then we're going to calculate something called the isothermal efficiency. Basically what we're going to see is that it takes more work to compress the air than if it was an isothermal process, and the isothermal efficiency tells us how close we are to having an isothermal process. Okay, so to begin we're going to calculate a couple of parameters that are going to help us with some of these calculations. Now down in the bottom left hand corner we have a variable C, which is known as the clearance ratio, and we have a variable R subscript P, which is known as the compression ratio. Now our clearance ratio is the ratio between the clearance volume and the swept volume. Ideally, we would want that value to approach 0, meaning no volume or no air was being left behind in the cylinder. So a higher clearance ratio indicates that more air is being left behind in the cylinder. Well, in this case, we have our volumes specified in decimeters cubed. Now, because what we're calculating here is a ratio, we can actually work with decimeters cubed. Now, we would get exactly the same answer if we converted both of those to meters cubed, but just for simplicity at this stage, I'm going to keep each of those in decimeters cubed. So we have 0.25 over 2.65, giving us a clearance ratio equal to 0.09434. Now that value there is rounded to 5 decimal places, so when we do some of our subsequent calculations, I'm going to use the full calculator answer to avoid any rounding errors. Now our compression ratio then is the delivery pressure divided by the inlet pressure. So we have 10.75 divided by 1.01, giving us a compression ratio equal to 10.64356. Now once again that value is rounded to 5 decimal places, so when we do our calculations of polytropic work and isothermal work, which incorporate our compression ratio here and here, once again I'll make sure that I use the full calculator answer to avoid any excessive rounding errors. Okay, so now we've done those two preliminary calculations, we're going to go ahead and calculate our volumetric efficiency. And our volumetric efficiency can be found using the following formula. 1 minus the clearance ratio times the compression ratio to the power of 1 over n minus 1 inside our square brackets there. Now once again I'm going to use full calculator answers for my clearance ratio and my compression ratio. But for simplicity here, I'm going to write the rounded values. So we have 1 minus 0.09434. Compression ratio is 10.64356. To the power of 1 over n. Well, we've said that lowercase n, or our polytropic index, is 1.19. So we're going to raise that to the power of 1 over 1.19 minus 1. Now you need to take care here when you input this into your calculator. So recall that when we input our clearance ratio, we're inputting 0.25 over 2.65 here. And when we input our compression ratio, we're inputting 10.75 over 1.01. So when we input that into our calculator, we get a volumetric efficiency equal to 0.4060 or 40.6%. So we have a fairly low volumetric efficiency there because our clearance volume, or the volume that remains in the cylinder, is relatively high. We're going to look at an alternative method for calculating our volumetric efficiency in the next video. So we'll use all of the same parameters and we'll look to prove that our volumetric efficiency is 40.6%. And we'll be using our indicator diagram and our volumes at position 1 to 4 in order to determine that volumetric efficiency. But for now, let's continue with this example. We're going to determine our polytropic work and our isothermal work next. Now, the important thing to note this time is that we need to work in SI units because we want our work, or the work done, also to be given in SI units. Where we need to use SI units here then is for our pressures and also for our volumes, V1 minus V4. Now I'm going to make a note of our volumetric efficiency down in the bottom left-hand corner. We have volumetric efficiency equals 40.6%. Now the reason I'm going to make a note of that is because I want to bring back our PV diagram So we can understand what's meant by V1 minus V4 because it's a characteristic of our cylinder. Okay, so referring to our diagram on the screen here, we can see that V1 corresponds with a position here on our volume axis, and V4 corresponds with a location here on our volume axis. And as we can see, this distance, or the difference, V1 minus V4, is actually referred to as our induced volume. So we have another formula that's useful here for the volumetric efficiency, because the volumetric efficiency can also be found by doing the induced volume over the swept volume. So now we can see the significance of our volumetric efficiency because it's telling us how close our induced volume is to our swept volume. So in this instance, we have a volumetric efficiency of 40.6. That means our induced volume, or the volume we're drawing into the cylinder, is only 40% of the swept volume. Now, the other reason this is useful is because we can use this formula to determine our induced volume. And the reason we want to know the induced volume is because V1 minus V4 at the end of our polytropic work calculation and V1 minus V4 at the end of our isothermal work calculation is simply the induced volume. So if we determine our induced volume and we convert that induced volume to meters cubed, then we can input that value in place of V1 minus V4 here and V1 minus V4 here. Our induced volume then is our volumetric efficiency as a decimal times our swept volume. All I've done there is multiply each side of our equation by the swept volume. V in then is our volumetric efficiency as a decimal, 0.406, times our swept volume of 2.65. Note that at this stage I'm still working in decimeters cubed, giving us an induced volume then equal to 1.07594 decimeters cubed. And as we can see there, our induced volume is under half our swept volume. So the volume that we're drawing into the cylinder is only 40% of the swept volume of that cylinder. Okay, so moving on to our calculations then for polytropic work and isothermal work. We have the polytropic work equals P1. Well, P1 is our inlet pressure, and we see in the top left-hand corner that is 1.01 bar. Well, recall that to get from bar to pascals, we multiply by 100,000, or times 10 to the 5, meaning P in pascals is 101,000, and that corresponds with atmospheric pressure. So we have 101,000, n over n minus 1, well n is 1.19, n minus 1 then is 0.19. We have our compression ratio. We could input this as 10.64356, but to avoid any rounding, I'm going to keep that as 10.75 over 1.01. The power here, note that it's the opposite way round to outside the bracket. It's n minus 1 on the top, so 0.19, and n on the bottom, 1.19. Minus 1, and we're multiplying that by the induced volume. Now, we said previously the induced volume was 1.07594 decimeters cubed, but we also said that there's 10 decimeters in every meter. Therefore, if we wanted to go from decimeters to meters, just making a note in the top right-hand corner, we would need to divide by 10. So 10 decimeters is 1 meter. But we're not going from decimeters to meters. We're going from decimeters cubed to meters cubed. Therefore, we need to divide by 10 cubed. 10 cubed is just 1,000, so we need to divide our induced volume in decimeters cubed by 1,000. Well, 1.07594 divided by 1,000 is 0.001076. So we need to take care when we input this into our calculators. And I would urge you to do this for yourself and also check it a couple of times to ensure that you can generate the same answer more than once. But when I input this into my calculator, I get a polytropic work value per cycle. And note this is every cycle because we're using the induced volume of our cylinder. And that value comes out to be 312.27 joules. So we've already said that we would expect our isothermal work to be less because the isothermal work is the amount of work that would be required in order to compress one cylinder's worth of gas if we had a constant temperature process. So we would expect this value to be less than 312.27. Now, once again, we work in SI units, so our pressure in remains as 101,000. We have times natural log, the compression ratio, 10.75 over 1.01, times our swept volume, 0.001076, giving us an isothermal work per cycle equal to 257.01 joules. So we can see there, if this was an isothermal compression, it would take 257 joules to compress and expel our air, whereas as this is a polytropic process, it's actually taking 312.27 joules. So next then, we're going to clear some space. We're going to calculate our isothermal efficiency, our free air delivery, and the indicated power or the power being consumed by this compressor. Okay, so our isothermal efficiency is straightforward to calculate because it's our isothermal work, or the work done to compress the air per cycle if this was an isothermal process, divided by the polytropic work, which is the work done compressing the gas, assuming this is a polytropic process. We have those two values there. Our isothermal work then is 257.01, and our polytropic work is 312.27, giving us an isothermal efficiency equal to 0.823 or 82.3%. Now we've calculated the work required in order to compress the air during one cycle, and there we found the polytropic work to be 312.27. But if we wanted to determine the power required by our compressor, then we would need to consider how many cycles were being done every second, or how much air was being compressed and delivered every second. Recall that power is just work done every second. So what we're going to do is firstly calculate something called the free air delivery, and the free air delivery is the amount of air that passes through the compressor in a given period of time. So the free air delivery is our induced volume, which is the amount of air that passes through the cylinder per cycle, and we need to consider the number of cycles every second. Well, we know how many cycles we're doing every minute because we have our speed specified here as 450 revolutions per minute. So what we would need to do then is multiply by the number of cycles every minute divided by 60, because that would give us the number of complete cycles every second. Our free air delivery then is our induced volume of 0.001076. Note that we're working in meters cubed there, times our number of cycles every minute divided by the number of seconds in a minute, giving us a free air delivery then equal to 0.00 0.0807. That's going to be meters cubed every second. So every second we have 0.00807 meters cubed of air passing through our cylinder. Now note that that's roughly 7.5 cycles every second. So every second we compress 7.5 full cylinders of air. So if we want to calculate our polytropic power then we can use our work done per cycle as a starting point. Let's clear some space and then we'll look at how we can modify that formula. Okay, so instead of calculating the work done per cycle, we're going to calculate the power. And it's the polytropic power. Our inlet pressure remains the same, as do our polytropic index, our compression ratio, and here our polytropic index. Those values all remain constant. The difference is the amount of air that's travelling through the system. So instead of our induced volume, V1 minus V4, we're going to use our free air delivery. Free air delivery is the amount of air passing through the system per second. So that's the only modification that we need to make to that formula in order to determine the work done per second instead of the work done per cycle. And once again, we're going to expect it to be roughly 7.5 times the polytropic work that we calculated previously. So let's input some values. We have 101,000. N is 1.19. So n minus 1 is 0.19. Our compression ratio is 10.75 over 1.01. That is a ratio, so we don't need to convert that to SI units. To the power of n minus 1, so we have 0.19 over n 1.19 minus 1 times our free air delivery 0.00807. Okay, so running that through the calculator gives us a work done every second equal to 2342 joules per second. Well, joules per second are watts, so we have 2342 watts. Or expressing that in kilowatts, we have 2.342 kilowatts of power. So our compressor here is consuming 2.342 kilowatts of power in order to compress and deliver our air into the air receiver. So just to summarise then, in this video we've calculated the volumetric efficiency, which tells us how much air passes through our cylinder when compared to the swept volume of the cylinder. We've calculated our polytropic work and our isothermal work. Polytropic work assumes that we have polytropic compression processes, whereas isothermal assumes that we have isothermal or constant temperature processes. And we've calculated our isothermal efficiency, which compares the isothermal work, or the constant temperature work, to the polytropic work. And it tells us how close our process is to isothermal. Next, we calculated our free air delivery, which is the amount of air passing through our cylinder every second. And then we use that to calculate the power consumed by our compressor as it compresses and delivers air into our receiver or into our system. In the next video, we're going to look at an alternative method for evaluating the volumetric efficiency, and we're going to compare that with the volumetric efficiency obtained here, down in the bottom left-hand corner, of 40.6%. And ideally, although the two methods differ, we should arrive at the same volumetric efficiency of 40.6%.